All right, let's jump right into this explainer. We're unpacking a really fascinating research paper today on how to turn everyday commodity CPUs into absolute AI powerhouses. We're constantly hearing about this massive scramble for highly specialized, super scarce GPU accelerators, right? But what if the key to incredibly efficient AI inference is literally already sitting in your server racks? Today, we're exploring a massive breakthrough in cache-resident execution that completely flips the script on how we process large language models.
So when we look at massive models like Llama, we all know they can be slow and super resource intensive. Now, you might think running them takes forever because of all that complex math or the billions of calculations happening behind the scenes. But actually, that's a total misconception.
The reality is actually much more mundane, but, well, way harder to fix. It's not the math, it is the memory. As the research points out, LLM inference is completely dominated by data movement. The real culprit here is the time it takes to shuttle data back and forth across the memory hierarchy. See, because there's very little data reuse for each token generated, the system's arithmetic intensity is surprisingly low. Honestly, it's spending all its time just fetching data, rather than actually computing it.
Okay, here is how we're going to break down this technical mystery today. First, the AI memory bottleneck. 2, the KV cache pressure paradox. 3, decoupling weights and attention. 4, rethinking sub-operator synchronization. And finally, number 5, massive speedups on CPUs. Let's get into it. Section 1, the AI memory bottleneck. Bottom line here, moving heavy data is the absolute enemy of speed.
Think about it like this. To decode a single token, a transformer model has to drag activated model weights and attention states through the processor over and over, layer by agonizing layer. The obvious fix? Just keep the data right next to the processor. This brings us to the CPU's last level cache, or LLC. Thanks to recent advancements in 3D stacked cache tech, modern server CPUs now have gigabyte-scale last-level caches. I like to think of the LLC as a super-fast workbench. If you can keep your tools and your materials right there on the bench, your work absolutely flies. But there's a catch. Space on this workbench is incredibly tight. You literally just can't fit everything. Which brings us to Section 2, the KV cache pressure paradox. This is all about why buying more cache doesn't simply fix the problem.
Now, you might be thinking, hey, to fit a massive model, why not just partition it across more CPUs? That way, each one has a smaller, manageable chunk of the weights on its workbench, right? Well, doing that triggers a massive hidden problem. To understand why, we've got to talk about the KV cache. Going back to our analogy, if the model weights are the heavy static tools on your workbench, the KV cache is the project material itself. It's a runtime state dedicated to a single query. And here's the kicker. It dynamically grows larger with every single token you process. They are totally different beasts. Weights are static and reusable. The KV cache is dynamic and sequence-specific.
So here is the paradox. Naively mixing those static weights with that ever-growing KV cache completely overwhelms the system. Here's what happens. To fit massive model weights on the workbench, you have to split the pipeline across more nodes. Fair enough. But to keep that deeper pipeline busy, you now have to process way more in-flight tokens simultaneously. And more in-flight tokens means a proportionally massive ballooning of the KV cache on every single node. Eventually, this bloated KV cache literally knocks your reusable model weights right off the high-speed cache and back into the slow main memory. It's a frustrating zero-sum game.
Moving to Section 3, decoupling weights and attention. This is what the researchers call the elegant separation of powers.
Since weights and attention behave so completely differently, the researchers came up with this brilliant concept, weight-attention decoupling, or WA decoupling. Think about it. Weight-centric operators repeatedly access static weights, but they don't care at all about the growing KV state. On the flip side, attention operators only care about the KV cache and never even touch the static weights. So instead of that chaotic, overflowing workbench where everything is fighting for space, they threw out the old way. The new way completely isolates them into dedicated resource domains. Memory and compute are finally allocated based on how they actually behave.
Here is exactly how it works in practice. Step 1. You dedicate your first node purely to weight-centric operators. Its whole job is just prioritizing keeping those reusable weights resident in its cache. Step 2. The output embeddings, which by the way are tiny, just kilobyte scale, are routed over to node 2. Step 3. Node 2 acts as your dedicated attention node. It manages that whole sprawling KV cache and processes attention entirely on its own. It's a beautiful setup because now your KV capacity can scale completely independently without ever evicting those precious, reusable weights from the high-speed cache.
All right, Section 4, rethinking sub-operator synchronization. Basically, eliminating the traffic jams.
Okay, so once your data is running lightning fast on the cache, guess what? Standard synchronization becomes your brand new biggest bottleneck. Traditional systems use this operator-centric execution model where they literally force every single parallel part of an operator to stop and wait for a global sync before moving to the next step. It's like a massive, unnecessary traffic jam. But this new design, it utilizes true sub-operator data dependencies. It just completely throws away that clunky global barrier and looks very practically at what actually needs to wait for what.
Which brings us to sub-operator asynchronicity. In multi-head attention, one head doesn't actually depend on the completion of the others, right? So by allowing independent attention heads to just emit a quick signal when they're ready, we completely dissolve that global traffic jam. All the downstream computation is now driven by these independent signals. And for the parts that do require merging, they use a bounded tree-based reduction. This basically ensures that data is streamed exactly when needed and not a millisecond before, which perfectly preserves that crucial cache bandwidth.
Let's look at the payoff in Section 5, massive speedups on CPUs, the real-world impact of Cache-Resident Inference.
So let's see how these two brilliant innovations, weight decoupling and sub-operator asynchronicity, combine to just completely transform standard CPU hardware. As you can see, the data really proves the massive throughput and latency gains across different Llama models. But you know what the most striking thing is? It's how intense the improvements are in the small batch regime. For real-world, user-facing AI applications, you are almost always serving small batches because you have to keep latency low. And that is precisely where this new architecture absolutely shines the brightest.
To put a hard number on it, under a validated analytical model, this architecture achieves up to an astonishing 13.9 times speedup in time per output token compared to standard llama.cpp. No joke, 13.9 times. Even when they measured it directly end-to-end on real deployed systems, they were still seeing up to 11.5 times speedups. Guys, this isn't just some minor incremental optimization. We're talking about a completely different league of performance for CPU-based inference here.
So what's the big picture? What should you take away from this explainer? Well, first, AI memory bottlenecks absolutely can be solved on commodity hardware. Second, by truly understanding the fundamental difference between static weights and a growing KV cache, YA decoupling stops the cache from cannibalizing itself. Third, rethinking synchronization down to the sub-operator level completely eliminates those microsecond delays that honestly add up super quickly. Ultimately, it proves that your standard CPUs are incredibly viable for fast, efficient inference. Because right now, the entire tech industry is literally fighting tooth and nail over scarce, incredibly expensive GPU accelerators. But this research, it proves that your standard multi-socket CPU cluster, if it's cleverly optimized for cache residency, might just be the AI powerhouse you didn't even know you already had. So I'll leave you with this. Are commodity CPUs the untapped secret weapon of the AI revolution?